Hello, my name is Elisa Bosmans. This is my Physics 2211 Lab 2 of an object falling. In this lab, we measured and predicted the motion of a falling object being dropped from a given height, which then revealed the difference when calculating with and without drag. Some assumptions that were made would be that the force of gravity is constant and that drag forces on the object were constant as well, and the object didn't change orientation. Like if you had a falling crumpled up piece of paper, which I had, it didn't change direction to where it would have different drag on different sides. And then the computational model with drag accurately predicted the motion of a falling object. And then some fundamental principles were Newton's second law, general kinematics, in that sense, gravity, and drag, which is basically air friction, and like the force that's pushing up on the object when it is falling, like it's in the opposite direction of gravity. And then we compared the object falling in the simulator with two different factors, factoring air friction and ignoring air friction, or with drag, which is the opposite force to gravity. But some details of this experiment. The experiment component was conducted by video footage of an object falling across the screen, and then a tracker software was used to track the motion of a ball at 3 millisecond increments to calculate velocity and distance traveled. The possible error could include environmental factors like friction between the object and the surface, or human error, or object and air, I guess, or if something else hit it. And then changing orientation in space, and the system was the object and the surroundings. The surroundings was everything else other than the object. The initial conditions as an object being dropped. This is what it looked like. This is the crumpled up piece of paper. This was its path of motion across the screen. And then I set the coordinates like this so that all the values would look like that. And I could make a nice graph. Some details of the computation. Computational component was conducted through graphing software coded in Python that demonstrated movement of an object at a constant speed. The code and its respective output will be shown on the following slide. I'm not sure there are any major sources of error when dealing with a computer-generated simulation, just proper calibration and rounding errors. This is what my graph looked like. I set the velocity going up so I could graph, or the motion going up so I could graph the curve with the positive values. And then this was the initial time, because I started the video late when I took it. And then this was my delta t, the initial position vector, because the position was not directly on the y-axis when I dropped it. And you can see here the equations for, this is the equation for drag force right here. And this is the equation for gravity, or the weight of the object. And then this is updating the ball's velocity and the ball's position in that code. And then that outputs this, and which I don't have another picture where it displays drag, but you understand. This is me graphing it. This is my graph. I'm not entirely sure what happened here with the data, but this is what it looks like. The curve goes up in this kind of fashion because gravity is accelerating the object, so it's not a constant motion, so the graph would be curved. I'm not sure why this blue graph does not look as curved as the red one, but yeah, you get the gist. And then the additional questions: prediction of terminal velocity. The yellow model takes drag into account, was able to predict the full motion of the ball, including terminal velocity. Terminal velocity was reached when F net equals 0. Which means that the gravitational pull and the drag pull equal each other, or not pull, the force of gravity and the force of drag were equal, so that the object cannot change and now is moving at a constant speed. Individual force calculations and programs determine when Vmax is reached, and if if the object is thrown, Vmax would be reached sooner than when the object was dropped from rest. This can be confirmed by changing the initial velocity conditions in the computational models to include compared an experimental and computational model of an object, not with constant velocity, that is being dropped, to demonstrate fundamental concepts in kinematics in the second law.